Hello and welcome back to Nunley Math. I'm your host, Aaron Nunley. We're working our way quickly through several of our different basic functions forms. Today we're looking at the exponential function. The exponential function, I know it's an exponential function because this x right here is located as an exponent. So since the x is an exponent, we call this an exponential function. And just like the others, I'm going to create some domain values. I'm going to stick them into the function. I'm going to see what the output is. We're going to graph those on our coordinate plane, and we're going to have a conversation about what that looks like. Just like the others, at this point you should be getting pretty good at substituting numbers in, so I'm going to do this pretty quickly. I would suggest you do it on your own first and then restart the video so you can see how I do it and compare the two. If x is a 0, anything to the 0 power is a 1 plus 3 makes 4. This is the coordinate 0, 4. It might be worth making a note to yourself, if you did not already know this, that any number to the 0 power is 1. That is something you are not going to want to forget. It has a huge impact on what we're doing here today. And I graph that point. If I put in a 1, 2 to the first power is 2, plus 3 makes 6. Oh, sorry, 1 plus 3 is 5. Wow, that was almost really bad. 1, 5. If I put in a 2, 2 to the second is 4, plus 3 makes 7. If I put in a 3, 2 to the third plus 3 is 8, plus 3 is 11. And I can see clearly that this is going up and to the right. Notice it grew by 1, then it grew by 2, then it grew by 4. That is significant, and we'll talk about that at a later point in time, but we're going to hold off on that for now. Since I know which direction this is going, and since I've run out of room on my coordinate plane, I'm going to start working my way the other direction. If x is a negative 1, a lot of my students struggle with 2 to the negative 1 power. Do you know how to do that? If we think back to our rules for exponents, a negative exponent tells us to use the reciprocal of the base. Remember, this is 2 over 1, so the reciprocal would be 1/2 to the first power. 1/2 plus 3 is 3½. Negative 1, comma, 3½. I'm going to go ahead and put a dot here at 3½. Let's do the next one, negative 2. If I have a 2 to the negative second power, the negative sign says once again to use the reciprocal. This time it's 1/2 squared, which is 1/4. 1/4 plus 3 is 3¼ You get negative 2, comma, 3¼ And I'll go ahead and do negative 3. I'll leave it to you on your own to realize that that is 1/8, which makes this 3 1/8. Negative 3, comma, 3 1/8. So I'm going to go ahead and graph those. Negative 2, 3 1/4. Negative 2, 3 1/8. Are you noticing something interesting about that graph? Let me help you with that. If I put in a negative 4, I get 1/16. 3 1/16. So negative 4, comma, 3 1/16 goes right here. Can you predict without doing computation what a negative 5 would be? Take a look again. 1/2, 4th, 8th, 16th. Negative 5 is actually going to be 3 1/32. You see, every time I increase, or I should say decrease this, negative 1, negative 2, negative 3, negative 4, this value gets cut in half again. It was a 1/2, it was a 4th, it was an 8th, it was a 16th, it was a 32nd, and that pattern is going to continue on and on forever. 1/64th, 1/128th, 1/256th, 1/512th, and so on and so forth, forever and ever. This graph, in fact, is going to flatten out right here. It never becomes perfectly flat, but it does continue on and on forever in that direction. Now you're going to start to hear just a little bit of noise in the background. I have some students getting ready to come in. They're going to come in quietly so they don't interfere with what we're doing here. But we're going to go ahead and get this wrapped up. This line, or this curve, will approach this horizontal line forever and ever without crossing it. This line has a special name called an asymptote. An asymptote is a line you approach but never cross. In fact, down here I said the graph is a curve that will never go to or below the number 3. It will never go to or below the number 3. In fact, all exponential functions are curves with a line called an asymptote. They will approach but never cross. And I want to cross out that last word, line. You get an asymptote. That's a line you approach but never cross. Now, this asymptote is a horizontal line. All horizontal lines are described as y equals a number. This one happens to be at 3, so this horizontal asymptote is at the line y equals 3. Notice a few things about it. First of all, every exponential function is going to make a shape similar to this. Now, it could be steeper, could be less steep. The whole thing could be slid to the right or to the left. I could even flip the whole thing over, but it will always, always, always make that same shape. Notice that it does cross the y-axis, the y-intercept, at the point 0, 4. And you'll notice that it goes on forever and ever as I go to the right and to the left. That means my domain is all x as long as x is a real number. The range on this problem is interesting, though, because all f of x will work, or every y will work as long as I'm going up. But when I come down, you can see that it's never going to reach 3 or below. It's always going to be above that 3. So I would say my range is every number above a 3. Hopefully this has been helpful to you. Hopefully it's been useful to you. We do have 2 more of these we want to work our way through and have a conversation about. Make sure you tune in for those, and then we'll go through and we'll clarify a few other things about these types of functions for you. As always, make sure that you like and subscribe and leave me a comment in the comment section. Make sure you turn on your notifications so you don't miss out on anything that we are doing. And then make sure you come back. My students are here now. You guys want to say hello? So greetings from Mr. Nunley's class. You guys take care. Have a great day, all right? Bye-bye.